Okay, I don't know that we've got input. Do we have the display capture going? Okay, interesting. Okay. I guess that's happening. There's like a delay, I suppose. All right, that's fine. That seems like a security breach. I don't know how to not display that. I have no idea what people can see. We'll see if this works. Okay, so basically we're going to go through a past paper. This is the 2023 HL analysis and applications paper. We're not going to do the whole thing, but we will do it in parts. So this, I suppose, is part one. All right, we'll just do it. So function f is defined as follows. So we've got f of x is very thick here. F of x is 7x plus 7 over 2x minus 4. We're told that x is a real number and not 2. Find the 0 of f of x. So by this they mean the root. That's just going to happen when the y value of our function is 0. And when we're looking at the y value, I'm basically only concerned with the numerator. The denominator can't be 0 anyway, but if the top part is 0, then the whole thing has to be equivalent to 0. So we're basically just interested in when will this be 0? That's going to happen when x is -1. Okay. So x is -1, we're going to have a point -1, 0. Then it says for the graph, write down the equation of the vertical asymptote and the horizontal asymptote. So the vertical asymptote here is the easiest. We are always going to get a vertical asymptote on a graph when I have an x value that's invalid. So what I'm concerned about here, because we've got the fraction, is that I would end up dividing by 0. That tells me that 2x minus 4 cannot be 0, which tells me that 2x cannot be 4, which tells me that x cannot be 2. You can have a hole. That only happens though if you cancel, right? So I said always a vertical asymptote when you have an invalid x value. That's not strictly true. If they cancel from a rational function, you're going to have a hole rather than a vertical asymptote. The horizontal asymptote is all about end behavior. And actually, you can have situations where you cross a horizontal asymptote, so it's not strictly a line that you never touch, but it's really about what happens when we have very large values for x. So as x approaches infinity, which is just a way of saying as x gets bigger, what's going to happen to this function? Well, I can really just go off the leading terms, right? So from looking at this, the +7 and the -4 are not going to be that relevant if we're putting very large values of x in. So if we're putting like 1 billion in for x, the fact that you're adding 7 to that doesn't make a big difference to the value. So you end up just evaluating the limit as we have 7x over 2x, and that will simplify to just 7 over 2. So really, like, once you're comfortable with this, you're just looking at the numbers in front of the x, basically. So our horizontal asymptote is going to happen when y is 7 over 2, and then we're going to have a vertical asymptote when x is 2. So those would be our values. Then it says find the inverse function. Okay, so we're just going to swap basically our x and our y values. So if we think this is f of x, 7x plus 7, this is going to be 2x minus 4. When we're taking an inverse, we're basically swapping the domain and the range. So the value that is currently our y, our output value, will become an input value, and the values that are currently inputs become outputs. So we represent that by swapping them, and then we can rearrange. And when we have something like this where y is appearing twice, this can sometimes throw people off. We're just going to distribute it. So the way that we're going to get just one y is we're going to put all the terms that have a y together. So we're going to have 2yx minus 7y. We're going to have 4x plus 7. And then we can factor the y out. So the y comes out and we just have 2x minus 7. On the other side, we've got 4x plus 7. Then we get the inverse function, which will just be 4x plus 7 over 2x minus 7, like that. All right, so the first problem, pretty straightforward. Am I going to have to do something with a calculator? That would be annoying. So on Monday, we've got a sample of 40 visitors who are randomly selected to live in the park. They're asked how many times that day they had been on a ride called the Dragon. This information is summarized in the following frequency table. Cool. It can be assumed that this table is representative of all visitors at the park. Following day, on the following day, Tuesday, we estimate the probability that each figure will ride the dragon and the expected number of times each visitor will ride the dragon. Okay, well, this is the data for the Monday. I think from an estimate standpoint, we're assuming that this is carrying over, basically. That the proportions will remain the same because we've been told that the sample will be representative of all visitors. So if we're interested in the probability that someone randomly selected will ride the dragon, we're just going to add these values up, but we're going to multiply it by the number of times that they join, right? So we would be doing something like, I'm going to go ahead and do this in Desmos. Desmos, and I want scientific. So 6 times 0 is 0. And then 1, we're going to have 1 times 16. We're going to have 13 times 2. So we're just basically how many total rides of the dragon are occurring. We do that by multiplying these values up. And then I'm going to divide the whole thing by the 40 visitors that come in. So on average, everyone is going to be riding the dragon 1.5 times. The expected number of times a visitor will ride the dragon will be 1.5. So the probability, okay, so I've answered the second part. The probability randomly selected visitor will ride the dragon. So here I need to categorize it as how many people are, or how frequently are people not riding the dragon, and I'll take that away from the total. So we would have 34 over 40, basically 0.85 is the probability that someone rides the dragon. Because we've removed the 6 instances where that doesn't happen. So 34 of the 40 visitors that we've recorded have ridden the dragon, and we assume that's going to be consistent. So it says it's known that 1,000 visitors will attend the amusement park on Tuesday. Dragon can carry a maximum of 10 people each time it runs. Estimate the number of times the dragon must run to satisfy demand. So if on the expected value that we're getting is 1.5 per visitor, I'm expecting 1,500 rides, basically, across those 1,000 visitors. And if it can carry a maximum of 10 people, I'm expecting 150 runs, I guess would be the word. Okay. So far, pretty straightforward. Okay, so now we're saying solve cosine x of 2x equals sine of x. All right, so we're expecting to actually get solutions. Okay, so cosine x, cosine 2x equals sine x. So this is pretty clearly going to be a case where we're going to want to use a double angle. Whenever I have something where I've got different values within sine or cosine functions, the first priority is always going to be to get the values of x to be the same, because otherwise it's very hard to solve the problems. That becomes kind of the first order priority over anything else, really. And the one that I'm going to use here, we've got a few different options for the identity for cosine 2x, but given we've already got a sine of x, I'm going to use 1 minus 2 sine squared of x equals sine of x. And this is going to give me a hidden quadratic, right? So we've got a square here. This is unsquared. So we end up with 2 sine squared x plus sine x minus 1 equals 0. And then this becomes a little bit difficult to solve as a factor. Does it? Minus 2? No, it doesn't. Ignore me. To factor this, you could do AC method. You could also probably recognize that it's going to be 2 sine x and sine x, and then it's going to be 1 and minus 1, and the only question is like, which way around does the 1 and the minus 1 go? Since I've got a positive value here, I'm expecting I want the 2 sine to be positive, so I'm going to make this plus 1, so that when we multiply it out, we get 2 sine x. And I'll have minus 1 here, that way we get 2 sine x minus sine x. So sine x is either 1/2, or sine x is going to be minus 1. And then since we're dealing with this domain, minus pi x pi, that's going to restrict the kind of values that we get. So minus 1 between pi and minus pi, we're not really, because if you think sine is like this, right? Sine looks like this. So you've got a solution here at 3 pi over 2. That would be minus 1. And I've got a solution here at negative pi over 2. So we're not going to get a positive solution for this, but we will get negative pi over 2 as one of our options. So we'll say x is negative pi over 2. And then we're going to have sine of 1/2, which is going to give us pi over 6, which is valid. Okay, let's look here. Okay. Find the range of possible values of k such that e to the power of 2x plus ln k equals 3e to the x has at least one real solution. So we're saying e to the 2x plus ln k is 3e to the x. So this is very similar to the last problem, actually. This is also a hidden quadratic, because I can represent, if I think e to the 2x, because of the multiplication rule with the indices, I could write that like this. So we're thinking in terms of, basically, it's a quadratic where we can solve for, so you can do a substitution if you want, right? Sometimes people find it easier if you say, a is equal to ex. But we can also just solve it without. So get everything on to one side. If we're saying there's going to be one real solution, I'm saying that the discriminant is going to be equivalent to 0. So whenever we've got, something that's specifying a number of solutions, telling me there's no solutions, one solution, two solution, it's a discriminant problem, like 99% of the time. So our b value here is 3, negative 3. So this is going to be 9 minus 4, and we've got 1 and ln k. So it's like minus 4 ln k equals 0. And so we get basically 9 over 4 equals ln k. And then this is going to be basically like e to the power of 9/4 is k. Ooh. Something's happening on my phone. I'm being told to go to bed, which I should not be doing. Okay, yeah, is that correct? E to the 9/4 is k, yeah. Find the range of possible values for k such that we have one solution. Okay, so it's saying range of values such that we have, it's at least one. Terrible mistake. So greater than or equal to 0. So we'll just fill that in. Greater than or equal to 0, greater than or equal to 0. I've got to be slightly careful here when I'm rearranging a natural logarithm like this. This can be a little bit tricky because I don't necessarily preserve the inequality just in the way that you would expect. I prefer to kind of think this through. So if we're saying that we want ln k to basically be smaller than this, that's going to happen when the e to the 9/4k becomes smaller. So we're going to have something like this. But there's another component that we also need to consider, which is because we're dealing with natural logarithms, k has a minimum value, which is 0. So I need to include that as well. Because I can't take a natural logarithm of a negative number, e ultimately is approximately 2.71. There's no power I can raise 2.71 to that's going to be a negative value. So k itself has to be between 0 and the sort of upper limit value that we're getting. There's a lot of trig in this test. All right, so the function f is defined by f of x is sine qx, where q is greater than 0. The following diagram shows parts of the graph for f, 0 to 4m, where x is in radians, there are x-intercepts 0, 2m, and 4m. Okay, cool. Find an expression for m in terms of q. Okay, so what this is playing with, that q is going to be a domain transformation. It's affecting our x values. And like most x transformations, it's going to be basically doing the opposite of maybe what you would intuitively expect. So it's going to take our x points and divide them by q, basically. So what I can do, probably the simplest way to do this, is displaying a full period for sine here. Under normal circumstances, a full period would be 2 pi. But the way we can think about it is if I divide that by q, which is how my transformation works, that should equal the period that's displayed here, which is 4m. And then I can basically end up with pi over 2m is q, which is what they're looking for. Find an expression for m in terms of q. 4m. Yeah. So basically it's been transformed, right? Q has a value of m in it, which is why we're ending up with an x-axis that has all of these m's in it. Then we've got a function g is defined by g of x. There's all sorts of other stuff going on. Okay. What's good here, though, is q has already been applied as a transformation to the function that we're looking at. So it says on the axis above, sketch the graph of q. Ultimately, this graph of g, sorry. Ultimately, this is asking us to apply the existing transformations. So two things are going to happen. I'm going to do the x values first. I'll screenshot it here. Oh, am I allowed to do that? Should be. Okay. That way I can draw on it. I'll put this over. So two transformations. I'm going to do the x-intercepts first. I always like to work with those first, mainly because we have no y values. So whatever's happening with the y value is almost irrelevant. So if we take a point that's like 2m, that's going to be affected by the fact that we're multiplying we've got like the 2/3 and then the qx within our sign. So we're basically adding in an extra transformation, multiplying by 2/3. But again, because it's an x transformation, it does the opposite. So we're multiplying by 3 over 2, which means this point that's currently 2m is going to become 3m. This point that's currently 4m is going to become 6m. And then the other thing that's happening is the points that were here, for example, the y value of that maximum point is now going to be at 3 because we're just multiplying our y values by 3. So it's not going to go directly up because the x value here, the m, is also being affected by the 3 over 2. So we end up at 3 over 2m, which is sort of here-ish. So we're going to have a point. Oh, it's a little high, but we're going to have a point here at 3m over 2, comma 3. And then our other point is going to be sort of here and the negative. So our sketch should look something like this. I've sort of placed that dock slightly haphazardly, but you get the idea. We're stretching horizontally and we're stretching vertically as well. And we get this new function as a result. Okie dokie, equilateral triangle. The side lengths of an equilateral triangle. I feel like this has been a fairly easy test, I won't lie. I feel like for a higher level, I've seen worse. Here. Okay, so the side lengths x of an equilateral triangle are increasing at a rate of 4 centimeters per second. Find the rate at which the area of the triangle is increasing when the side lengths are 5√3. So this is kind of a related rates problem, right? And what would be helpful is, love a drawing, let's designate the side lengths x. Well, because they've told us to. Great minds think alike, I suppose. So that's the length. When it says that they're increasing at a rate of 4 centimeters, this is per second, right? So they're giving us a hint about what the derivative is related to. But I would also expect, if they didn't tell me that, I would assume dx dt. That's kind of the default. So that's the rate of change. It's increasing, so I'll make it positive. So it's going to be, technically, I'll have the units, but 4 is our derivative here. Find the rate at which the area, so we're interested in dA dt. is increasing when the side lengths are 5 root 3. So we're interested in when x is 5 root 3. So what I need ultimately here is I need an equation that is going to relate the it's going to relate the triangle to the area to the side length. Got those words out eventually. And you could do this using trig if you wanted. You could do this using height. The important thing is, because it's an equilateral triangle, all of these corners are going to be 60 degrees, and this is going to be 30 degrees. So we can think about, if we take this like cutout of the triangle here, this is x over 2, and this is going to be x over 2 root 3. So that becomes a core component of our area, because our area is going to be 1/2 base times height. And this will simplify to, we're going to have basically root 3 over 4x squared would be our area. The reason this is important is, in order for my rate of change for x to have any kind of bearing on my rate of change for a, I need to understand the relationship between those two variables geometrically. So this is their geometric relationship. And if I differentiate this using implicit differentiation, so I'm going to differentiate this with respect to time. So a, therefore, is dA dt. Now, what's important about implicit differentiation, we're basically assuming that a and x are both functions of time, that they have some sort of relationship to time, but we don't know what the function is. We don't know if it's like a cosine or a square or a logarithm or what. So we're going to differentiate them like they're functions. So here where it's x squared, I'm treating that like it's a function that's been squared, and therefore I need to differentiate with the chain rule. So this is going to be like root 3 over 2x. That would be your standard derivative, but then my chain is going to be dx dt. So because I don't know what x is in terms of time, I therefore can't really know what dx dt is. Well, I mean, aside from the constant, but for the purposes of setting this up. So I just write this as, descriptively, I say the derivative of x with respect to time. But I can plug values in because I know two values now. I know x is meant to be 5 root 3, and I know the dx dt is 4. So I can just plug these in. Root 3 over 2, x is 5 root 3, this is 4. And so we get 5 times 3, 15. 15 times 4, 60. 60 over 2, 30 centimeters per second. And it's an area, so it's going to be centimeters per second squared. So this side length is increasing by 4 centimeters. This is happening to all the sides simultaneously. That's causing a constant rate of increase, or certainly at this moment, it's not constant in general, but at this moment, an instantaneous rate of change of 30 centimeters per second. All right, well, so there's some more stuff going on here, obviously. But I think I'm going to save that for next time, for tomorrow. So we'll wrap up here. It's very possible that actually this hasn't even recorded at all, or you can't see my screen or something, and it's been a disaster. So we may be coming back and actually just doing this again. But